Hello guys, in today's video I'm going to show you how you can calculate energy changes. So in the first video on chemical energetics we took a look at the meanings of exothermic and endothermic reactions, and we saw that exothermic reactions release heat, endothermic reactions take in heat. And in the second video we looked at how we can explain endothermic and exothermic reactions in terms of the energy contained within the bonds, and in particular the energy absorbed during bond breaking and released during bond formation. So just write it down now. We're going to calculate So in this video we will do some numerical calculations to concretely understand how the process of bond breaking and bond formation can result in endothermic or exothermic reactions. So a couple of conventions to start off. When energy is absorbed, when energy is absorbed, we denote that as plus energy. So absorb also means endothermic, and energy is absorbed when we break bonds. So breaking bonds is an endothermic reaction, hence we denote it using a plus sign. And when energy is released, we denote that using a minus sign, and release of energy is defined as exothermic, and energy is released when bonds kind of snap together, when atoms snap together to form bonds. So bond formation is an exothermic process, and the units for this energy is given in kilojoules per mole. So it's typical to say, if I'm forming a molar bond between two atoms, how much energy is absorbed or released. So in calculations it's important to understand that this energy is really the energy between two atoms, right? And we'll take a closer look at what that means in a second. So typically energies between atoms are given in the table of bond energies, and this table will show you the energies between any two atoms, so the bonds formed between two atoms, and how much energy is needed to absorb to break those bonds. So by convention these energies are positive. So I have a very short table here. If you look on the internet you'll find much longer tables, but this table will just is just for illustrative purposes and also to aid in our calculations in a little bit. So you can see here that the amount of energy required to break the bond between hydrogen and hydrogen is 436 kilojoules per mole, which means if I have a mole of hydrogen molecules, I'm going to need 436 joules to break those bonds. Now it's also important to realize that the same amount of energy will be released when the bonds form, right? So let's just write that down. So the energy to break the bonds is equal to the energy to form that same bond between the same pair of atoms. So 436 joules is required to break the HH bond here, and also 436 kilojoules of energy will be released when a mole of hydrogen atoms comes together with another mole of hydrogen atoms to form 1 mole of hydrogen molecules, right? So these energies are the same for the same pair of atoms, right? So let's head straight to an example and take a look at how we can calculate this. So I've come up with a series of steps that we'll need to follow, and I'll put that on the side here. Right, so calculating energy change. The first step is to write a balanced equation, and after that we need to draw an equation, to draw the equation to show all the bonds in the equation. Then the total energy change will be the energy absorbed, and remember energy in is always positive, minus the energy out to form the bonds. Because why minus? Because energy is released when we form the bonds. So if we take the numerical value of energy in minus the numerical value of energy out, that's going to give us the overall energy change in a reaction, and that would tell us whether the reaction is endo or exo, with positive being endo and negative being exo. So to start off, let's look at an example that we've already looked at in the previous 2 videos, which is the formation of hydrogen chloride from hydrogen and chlorine. So I will take hydrogen gas and react it with chlorine gas, and remember hydrogen chlorine always exist as diatomic molecules. They can't exist singly, they're not stable that way. So we're going to write H2 plus Cl2 to give me hydrogen chloride gas, and we need to balance it because I have 2 moles of 2 hydrogens here and 2 chlorines here, and only 1 hydrogen, 1 chlorine here. Putting a number out in front will balance that. Remember, you can't add numbers at the bottom, only numbers out in front of the whole molecule. And now to aid the calculation, we will draw all the bonds shown by this equation. So I have an H bond here, a Cl bond here, to give me HCl and another HCl, because I have 2 of them, so you can see 2 molecules here of HCl and HCl. Alright, and then now I count up the number of bonds and multiply them by the energies per mole of each bond. So let's take a look at the table here. I have 1 HH bond, so I will go ahead and do 1 HH bond, and how much energy is that? It's 436 kilojoules, so I'll just write 1 times 436 for each one, which results in 436 overall. And I have 1 of Cl here. Remember, these are the bonds that we are breaking, right? We're breaking bonds here. We're only breaking bonds in the reactants, not in the products. So I'm just going to write the reactants on here. And by looking at the table, we see that the Cl bond is 242 kilojoules per mole. So I'll write 242 there to give me 242 here. So the overall amount of energy required to break the bonds in the reactants, just the reactants, is going to be 876. So it's going to be 678 kilojoules to break per mole of these reactants, right? So since this energy is absorbed, I'm going to put a plus sign out in front. And now let's take a look at how much energy is being released when we form these 2 moles of hydrogen chloride here on the product side. So taking a look at my table again, I see that HCl has a bond energy of 431 kilojoules per mole, and since I have 2 of them, I'm going to do 2 times, let's write 2 HCl's here, so it's 2 times 431, which is 861. And since this energy is released because I'm forming bonds, I'm going to set a minus sign out there. Right, I beg your pardon, this is 862. Right, so the overall energy change is just the sum of these two energies, the energy that was taken in to form the bonds and the energy that was given out the energy taken in to break the bonds and the energy given out to form the bonds. So breaking is 678 and forming was 862. Therefore, I have an overall change of minus 184 kilojoules of energy in this reaction, right? So I can go back up here and say that my energy change, which we frequently denote by the letter delta H. So delta H for this reaction is minus 184 kilojoules. Now I've dropped the per moles because saying per mole is kind of vague now, because it's true I have a mole of hydrogen and a mole of chlorine, but then I have 2 moles of hydrogen chloride. So when you say per mole, which do you really mean? So I've just left it as that, which is to signify that if I take a mole of hydrogen and a mole of chlorine to form 2 moles of hydrogen chloride, then minus 184 kilojoules of energy will be released from this process. Hence, I can go ahead and draw the energy level diagram just for completeness. I'm just going to draw a really tiny one right here at the bottom. So I have energy here, and since this is an exothermic reaction, my reactants had a higher energy than the products because energy is taken out of the system, so the energy of the whole system will drop overall. And my reactants were hydrogen and chlorine, my products were HCl, and this energy here is minus 184 kilojoules. Right, so that is the overall energy change for this reaction, and we've showed how to do it by looking at the energies required to break the bonds and to form the bonds. So just to summarize, breaking bonds is positive, forming bonds is negative, and to find the overall change, you take the amount of energies required to break the bonds minus the amount of energies released when you form the bonds. And for the case of hydrogen reacting with chlorine to form hydrogen chloride, we found that minus 184 kilojoules of energy was released. So we can take a look at another example. This time we'll take a look at the decomposition of ammonia. So I'm going to have take ammonia gas and I'm going to heat it, right, to form nitrogen gas and hydrogen gas. And to balance this, because I have an odd number of hydrogens here and I can only ever get even numbers of hydrogens here, I'm going to try and multiply this by 2 to make it even, so that gives me 6 hydrogens, and I need 3 here to give me 6 hydrogens, and up with 2 nitrogens, and I already have 2 nitrogens there. So that is the balanced equation. Now I will show all bonds and draw them out. So I'm going to have 2 molecules of ammonia, and in each molecule of ammonia I have 1 nitrogen atom connected to 3 hydrogen atoms. So that's going to be 2 molecules of ammonia to form 1 molecule of nitrogen, and nitrogen has a triple bond in it. And I have 3 molecules of hydrogens, so I'll draw them all out like so. Okay, and to calculate the energy change, again what I do is I look for the amounts of energies taken in to break the bonds in the reactants minus the amount of energies released when I form bonds in the products. So by taking a look at this diagram here, it shows me all the bonds that I have. Let's count them up. This is an NH bond here, an NH bond, and an NH bond. So I have 3 NH bonds here and another 3 here. So that's 6 NH bonds. So I'm going to need to break 6 of these NH bonds, right? Just to make sure that you see that these are all NH bonds, let me just circle them this way. So NH, 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 and since it's the same molecule, I have 3 of the same, so it gives me a total of 6. So if I take 6 multiplied by, take a look at my table, and NH bond is 391 kilojoules, so that's going to give me a total of 2,346 kilojoules to break the bonds in the reactants. And now let's take a look at how much energy I need to form the bonds in the products. I have a bond of nitrogen-nitrogen triple bond, and that value is 946. It's quite high because it's a triple bond. Now, a common error here is to multiply this by 3. Don't do that, because you see 3 bonds here and you think, oh, this 946 is for each of those bonds, but in fact this 946 is to break all 3 bonds in the nitrogen-nitrogen triple bond. So be careful not to trip up there. Right, it's just going to be 946 for all of them. Right, and let's see what else I have. I have HH bonds, and I have 1, 2, 3 of them. So I'm going to have 3 of these HH bonds, which will be 3 times 436, and 3 times 436 is going to give me 1,308 kilojoules. So if I sum those together, I get 4,522. So it's 2,254 kilojoules, which is the energy released when I form the bonds. And because energy released is negative, I'm going to put a negative there, and this is a positive here. So this is the energy to break the bonds in the reactants, and this is the energy to form the bonds in the products. Hence, my overall energy change will be energy to break the bonds, which is 2346 plus, and minus energies to form the bond, 2254 kilojoules, rendering 92 kilojoules. Again, I've dropped per mole because it wouldn't make sense to say per mole anymore, so I don't need my table here. And therefore my overall energy change is plus 92 kilojoules, which means that this is an endothermic reaction, and it's overall going to cool the test tube. So if you touch the test tube, it's going to feel cool. So to finish this off, let's draw the energy level diagram, and because I end up absorbing energy, my products are going to end up with a higher energy level because you're taking energy into the system. So the system itself will increase its energy by 92 kilojoules here. So if I take 2 moles of ammonia and break it down into a mole of nitrogen and 3 moles of hydrogen, that's the energy change that results. 92 kilojoules of energy is absorbed by this reaction. So that was 2 quick examples to show you guys how you can look at bond energies to calculate the energy changes in a reaction. So just to recap, endothermic reactions are positive and breaking bonds absorb energy. Exothermic reactions are negative, and forming bonds are exothermic reactions. So the bond energy table will give you the energies of the bonds, and from there you can calculate the overall energy change in the reaction. So in the next video we will take a look at how we can use this to generate energy, how energy changes take place in the generation of energy in batteries, fuel cells, nuclear power, etc.